So section 2.2 is talking about polynomials of higher order degree. That may not feel very descriptive. Basically polynomials that have lots of ups and downs, so x cubed, x to the fourth, x to the fifth, those kind of polynomials. And what we're going to be looking at most specifically is how do you graph these or get a pretty approximate graph of these things without a calculator. And also finding zeros. Now that's not approximate, you need to be able to find the zeros exactly. But using that information to try to create a graph without a calculator. There's going to be a lot of non-calculator stuff this chapter, not really to punish you or torture you. It's so you really dig deep into what's going on with these functions and understand them better. I don't think you can really appreciate what's happening until the calculator's gone and you have to really work your way through it and really dig for clues to what's happening with these functions. So first thing is even or odd polynomials. So back earlier in the year we talked about even and odd functions, and I said don't get that confused with even and odd polynomials. So this is the deal that talks about end behavior. That's really what even and odd polynomials is all about. Do both ends point up, do both ends point down, or are they doing a disco dance like that? So that's really what even and odd polynomials is all about. It's all about the end behavior, and it's based on the leading coefficient. That's really all you've got to think about. So the most basic even odd polynomial, most basic odd polynomial is y equals x. If you think about what y equals x does, then you can figure out what x to the 23rd power is going to do. It's going to have the exact same end behavior. So y equals x looks like that. Left end's pointing down, right end's pointing up. So like I said, if it was x to the 23rd, the right end would still point up, left end would still point down. If this was y equals negative x, it would go the other direction. So the left would point up, right would point down. And your most basic even polynomial would be x squared. And we know that's a parabola, so both ends point up. And if it was a negative out front, both ends would point down. So if we have x to the 52nd power, both ends are going to point up. We know that. So that's really the whole point about even and odd polynomials. They help you understand what the end behavior is going to do. And the deeper we get into this, knowing the end behavior is going to tell you a lot of information. So let's do a little bit of algebra and find the zeros of this thing. So just to recap what a zero is. When you have a polynomial and it's crossing the x-axis, the y value would be 0 at those points, which means the function value, or f of x, is going to be 0 at those points. And what that means for your algebra is that you plug in 0 for your y value. And that's why you set these functions equal to 0. So we're in that kind of strange part of the year where we haven't proved the fundamental theorem of algebra, which makes all this stuff possible, everything I'm getting ready to do and why this works the way it does. So that's coming soon, it's coming in this chapter. But until we do, just rely back on those methods you've learned where you factor and do quadratic formula and all that good stuff. And then we'll prove why that has to work eventually. I know it's kind of backwards, but it's the way the book's laid out. And really, I think we're probably good to just kind of believe it, take it on faith for a little while, and then eventually prove it. So I'm going to leave that equal to 0. First up is this is a trinomial, but it's not really x to the square or x squared x constant. But they do have something in common. Every one of these has an x in common, so I'm going to factor that out. X to the fourth minus 6x squared plus 9. And I'm going to do something else here that you may not be comfortable with yet, but I suggest you go ahead and start working with it because you're going to get to something called the chain rule next year. And you're really going to want to do this U substitution. So I guess I might be getting ahead of myself. Let me break this down. Fundamental theorem of algebra, once we've got these things broken into factors, we can set each factor equal to 0. So x equals 0, that's a solution. Not much more to do there. This part's going to take a little bit more work. Now here's where the U substitution comes in. This is not x squared, this is not x. It's still a trinomial, it's in the right form, but it'd be really nice if that was something squared, and then the same variable not squared, and then that just a constant. So I'm going to do a U substitution. I'm going to come up with something, and it's almost always whatever's in the middle right here. I'm going to come up with something that I can substitute it in, and it's that variable squared, and then just that variable, and then the constant. So if u is x squared, that always sounds so grammatically incorrect. If u is x squared, then u squared would be x squared squared, so it'd be good. And this would be 6u. It should be a decimal. It just kind of got in there. So 6u, well, if u is x squared, then that's good. Plus 9 is 0. And we can do it however you need to. You can break the middle part down and do your x. You recognize that this is a perfect square trinomial. Hopefully, since you just worked on completing the square, that's kind of standing out to you. So this is u minus 3 squared. Now, at some point, we do have to solve for x because we made up the u. That was never in the beginning. We were finding these zeros, which are solutions, roots. We're finding out where x equal, what x values are where we're crossing the x axis here. So again, it's x value, x axis, not the u axis, not the u values. But before we take care of that, I'm going to go ahead and set this thing equal to 0. I'm going to go ahead and solve this. So u minus 3 squared, well, if I took a square to both sides, I took the square to 0, that would just be u, it would just be u minus 3 equals 0. Maybe another way, this might actually make more sense as to what we're trying to do. This is the same factor twice. So u minus 3 is squared, so 2 different times it equals 0. Well, it's kind of redundant. I don't have to keep doing that. So u would equal 3. And, I mean, that's going to be the same thing. So I'm just going to, unless you want to work it out twice, I'm good with you saying, you know what, these are the same. We don't have to work it out the second time. And then I don't want to give it away at the bottom here. X squared is actually 3. Which means that x is going to be plus or minus the square root of 3. Okay. There are my other two solutions. So 0 is a solution, and plus or minus the square root of 3 are my other two solutions. Now, hopefully, there's a little bell going off, a little alarm going off, and you remember something somewhere along the line about there was x to the 5th in the beginning, so weren't there supposed to be maybe 5 solutions to this problem? And yeah, technically there are. And that's why I left it factored this way. The x minus 3 squared, you had it 2 different times, which means that these 2 solutions here would have been repeated a second time. So those are both repeated solutions. Technically, that means we have 5 roots, 5 solutions. And again, we'll keep digging into how that works as we get into the algebra more. But that's what's happening. And I believe this is the way your book titles it, 0 multiplicity, so a fancy way to say repeated root. All right, I know this is kind of annoying, but since you started school, you learned how to do one thing, then you learned how to undo it. You learned addition, you learned how to subtract right after that. You learned how to multiply, and then they taught you how to divide. That never ends. The higher I went in math, the more doing and undoing I had to do. So that's exactly what's going to keep happening here. You just took a polynomial and broke it into its solutions. Now you're going to take the solutions and turn them into a polynomial. Now hopefully this is, again, I'll review, but I'll run through the process just in case so you remember how to do it. So here's our 3 zeros. And if you kind of run back through the problem, I'm just going to run backwards because that's, to me, the best way to see this. You had your solutions. Right before they were solutions, they were factors, and they were set equal to 0. And right before that, they were all a bunch of factors multiplied together. So up to this step, there are several, or well, two factors multiplied together. And then eventually, after that point, you can create a polynomial out of it. So there's kind of your step-by-step backwards process. So let's make them factors. X minus 2 would equal 0. X minus 3 would equal 0. X plus 1 would equal 0. And once they're all factors set equal to 0, they can be put together and multiplied. And all, again, equal to 0. I'm kind of doing some magic right there. That comes from fundamental theorem of algebra. We'll eventually explain that. And multiplication, I just recommend you pick 2 that look like they're not too bad to do together. And multiply those 2 together. And then bring the rest of the stuff down. So let's see, this would be x squared minus 2x minus 3x and minus 5x plus 6. And I'm just going to bring this term down. Multiply by x plus 1. So let's see if we can make this kind of methodical. It's really distributive property. So x squared times both terms. X squared times x is x cubed. X squared times 1 is x squared. All right, negative 5x times x is negative 5x squared. Negative 5x times 1 is minus 5x. And then take 6 and distribute. So plus 6 times x plus 6 times 1. And now let's combine what we can. X cubed minus 4x squared plus x plus 6. And that is our function. Now, this is probably okay, but if they told us to make an equation or function out of it, we really should make that happen. So write a polynomial function. You see that in the book. This is a polynomial expression, but not a function. So we really should put f of x over here so that we do have a function. That tells me I can plug in x values and then see what I get out. So let's run through graphing something without a calculator. And at the very end, I'm going to flash back to Desmos and have it graph so you can see if you're close. And I think that's okay to go back and check, but I really recommend that you do this without a calculator first, then go back and check. You've got to be able to do this without a calculator for assessments. So looking at the end behavior. All right, well, it's x cubed, and this is positive understood 1 in front. So that means it's going to be just like y equals x. The left side is going to point down, the right side is going to point up. So I'm going to just do a little like that. All right, and I'm not going to put it on the graph yet. I will in a second, right after I find the zeros. So zeros, well, let's see. If we set this equal to 0, and they have an x in common, so x squared minus 9. So x equals 0, x plus 3, and x minus 3 equals 0. All right, so 0 is a solution. That would become x equals negative 3. This would become x equals positive 3. Those are our zeros. Now, left end is going to point down, so I'm going to go ahead and from the leftmost 0, go down. From the rightmost 0, I'm going to go up, because that's what our end behaviors are going to look like. And that's actually something we'll get into in the next section. On your last 0, we'll refer to it as a boundary. After that point, we're never going to come back down across the x-axis again, because if this is guaranteed to be my last 0, then it's never going to come back down and cross. If it came back down, I have to cross somewhere else. And if this is the last place it crosses, it's going up forever. All right, and then test some other points to get the shape. So I'm going to do a few different points here. I'm going to try, let's try 1. That should be a pretty easy one. So f of 1, all right, well 1 cubed is 1. And then negative 9 times 1 is minus 9, so that'd be negative 8. So 1 negative 8 would be on there. F of 2, well, let's see, 2 cubed is 8. Negative 9 times 2 is negative 18, so that would be negative 10. All right. Now, calculus is going to give you a way to find those maximums. This is going to kind of peek out and drop down. Calculus gives you a way to find the maximums and minimums. And there's no point in me forcing you to do that by hand. There are some methods, but they rely on doing calculus. And when you get to calculus, you'll be able to do it simply anyway. So I'm never going to make you find maximums and minimums by hand, other than completing the square for a parabola, since that's an important process. But I'm never going to make you find the maximums and minimums by hand here. So just assume it does something like that, and probably make it a function where it doesn't backtrack on itself. Maybe a little smoother like that. So I can smooth that out a little bit. All right, and then for, we could look to see if this was an even or odd function. Then we could just duplicate some points. I don't know if that's really worth it at this point, but if I did f of negative 1, if I did negative 1 here, all right, well, negative 1 cubed is negative 1, and minus 9 times negative 1 is plus 9. So that would be 8. So 1 8. And I'm just going to tell you, and you can double check it if you want to, f of negative 2 would actually be 10. So looking like it's going to be an even function. Sorry, odd function, not even. All right, so that's a pretty gnarly looking curve to it. But that's the idea, and that's really all I'm looking for by hand. When you show me that you can do these by hand, That's it. That's all I need to see. I want to see that you can get the points where the zeros where they go. Zeros have to be definite. The end should be pointing the correct way. But in between, as long as it hits a few points that are definitely on the graph and you got the general shape, I'm good to go. So let me just flash back to the Desmos graph so you can see if it looks pretty close. And it looks like it probably is. One final thing to leave you with. When you get to 87 and 89, make sure you can do those without a calculator for parts A, B, and D. I believe the book might say something different, so I'm asking you to do those without a calculator.